On Phosphorescence in Quantum Chemistry by Daniel Bayrwalt, Katie Randolph, Leonardo Flores, and Daniel Girardo.
Phosphorescence is a form of photoluminescence, like fluorescence, but is less common and lasts far longer. Generally, after an electron is excited from the ground state to the excited state, it will undergo a series of deactivation mechanisms to return to the ground state. Most commonly is radiative transition, shown by arrow 2. This is fluorescence. However, if there is overlap in energy between the excited triplet state and singlet state, there can be a transition to the triplet state. This is shown by arrow 4, after which the excited electron can then radiate and deactivate, shown by arrow 5, to go from the excited triplet state back to the ground state. This process is called phosphorescence. Many people may have been first introduced to fluorescence and phosphorescence in the form of geological rocks and minerals. While fluorescence is very common, the same can't be said for phosphorescence. This uncommonality is very useful in phosphorescence spectrometry, where in a complex system you may analyze specifically for phosphorescing molecules, which can help not only in environmental systems, but also in organic systems. Phosphorescence has also shown to be a hindrance in concepts like transmission and scanning electron microscopy, where high-energy electrons can cause phosphorescence, creating artifacts on the surface of images.
Temperature phosphorescence is a trait that is typically associated with inorganic and transition metal complexes. Phosphorescence usually needs extreme conditions to occur in organic molecules such as cryogenic temperatures. There have been recent discoveries showing that organic materials can also exhibit room temperature phosphorescence, particularly when they come together in aggregates, especially in crystalline forms. Understanding the underlying mechanism behind RTP in organic aggregates is important. These new discoveries can also aid researchers in designing organic molecules that not only exhibit RTP, but also are efficient and long-lasting. Essentially, we are able to see how organic molecules can glow in the dark at room temperature and figure out how to make them shine brighter and last longer. This information can also be applied to other fields such as medical imaging. Using molecular dynamics, quantum mechanics, and molecular mechanics to explore the mechanisms behind aggregation-induced RTP, thermal vibration correlation functions, or TVCF, helped scientists calculate the rate constants of transitions of light in molecules. These rate constants are associated with the radiative and non-radiative decay and the intersystem crossing between electronic states. And using quantum mechanics and molecular mechanics at the excited state level of intermolecular interactions. Figure 1 shows photophosphorescence occurring along the pathway of S1 to Tn to T1 to S0. S1 and S0 are radiative and non-radiative decay rate constants, and T1 and T0 are intersystem crossing rate constants. Figure 3 shows low-lying excited states in the gas phase. The S1 state emerges as the n orbital, then transitions into the pi antibonding orbital. As S2 state moves from the pi orbital to the pi antibonding orbital, the n orbital is easily affected by electrostatic forces which create a charge separation. When shifting to the solid phase, the n orbital becomes stable due to the intermolecular electrostatic interactions. During this, the pi orbital also changes. Crystallization changed the S1 state. The energy in the n state and the pi antibonding energy increases, while the pi and the pi antibonding decrease in the gas phase. Then the S1 state turns to the pi and pi antibonding from the n and pi antibonding. This increases the phosphorescent rate. The mechanism of electrostatic interaction activated efficient phosphorescence helps in understanding the RTP behavior of compounds which have a dark and complete excited states, and this aids for other designs of efficient RTP systems. A key component of this technique involves altering aromatic substitutions in order to increase transition dipole moments in single state, thus speeding up the rate constant of phosphorescence. In conclusion, recent discoveries show that organic molecules can exhibit RTP when previously we only knew that they were able we only knew that we were able to see phosphorescence occur in them at extreme conditions. Understanding the mechanism behind RTP has been able to help scientists design organic molecules that are brighter and longer lasting, in which the implications can be applied to other fields of study.
Applications: Ultra-long organic phosphorescence. There has been a shift of focus from transition metal elements to metal-free organic phosphorescence. Ultra-long organic phosphorescence has its advantages, but also its cons. It's very flexible and easy to modify, but has a short lifetime only using organic material. A breakthrough in ultra-long organic phosphorescence with organic compounds was made with the accidental discovery of H-aggregated structures. This yielded a lifetime of 1.35 seconds. This opened a door to two approaches for ultra-long organic phosphorescence: facilitating spin-orbit coupling using heavy atoms and restrained non-radiative transition through rigid molecular environments. Intramolecular interactions drive ultra-long organic phosphorescence. Pi bond interactions stabilize triplet excitations. Hydrogen bonds suppress molecular motions, and halogen bonds enhance spin-orbital coupling. Ionic and covalent bonding produce bright ultra-long organic phosphorescence with unique properties. The manipulation of ultra-long organic phosphorescence material tunes the emission lifetime. This can be from intramolecular hydrogen bonding and the dp pi bonds. It can also stem from the changing of the chromophore environment, or the manipulation of molecular structure in crystals that also change the emission of color, which also affects the lifetime of ultra-long organic phosphorescence.
For applications in the medical field, phosphorescent compounds have recently been identified as having the ability to selectively tag certain molecules. This has been tested with formaldehyde in the lysosomes of mouse brain tissue, and as can be seen on the image on the left, it shows a clear signal in the presence of the target molecule. In the case of this tagging compound, it also changes color with varying concentrations of the target molecule, as shown by the center image. Phosphorescent compounds have also been shown to have the potential to be used for in vivo bioimaging. This application has been tested in a wide variety of compounds in live mice as indicated in the image on the right, and phosphorescent compounds show great promise for future use in medicine, as they have many desirable properties. These include longer emission lifetime, stable chemical and photochemical properties, larger Stokes shift, good water solubility, and good biocompatibility as compared to other currently used compounds.